let's make a session of Seoul ICM, and we have stellar lineup of speakers, a very exciting subject. And our first speaker is Professor Samson Shatashvili. He's from Trinity College of Dublin and currently at the Simon Center of Geometry and Physics.
Thank you. I want to thank organizers, of course, for inviting me to speak here. We were, of course, asked to give the talks, invited talks, understandable for broader audience, and I did try, but I'm not sure actually. Anyway, I want to start with something called beta gauge correspondence, which was accidentally discovered in the paper I wrote with Moore and Nekrasov long ago, and revived my paper with Gerasimov, and then Nekrasov and I think basically completed it. So the statement is like that. For every, at least known to me, quantum integrable system solved by beta ansatz, and I will explain all these things, of course, when time comes, there is a supersymmetric gauge theory with 4 supercharges, which I denote like this, such that the exact eigenstates correspond to supersymmetric vacua, and ring of commuting Hamiltonians is the same as twisted chiral ring in supersymmetric theory. Now, I don't say here exactly what dimensions I mean in supersymmetric gauge theory, because the way I will be thinking, and it's a good way to think about this in this topic, is that let's say if you're in 5 dimensions with 4 supercharges, 4 dimensions, 3 dimensions, you still think about those theories as 2-dimensional theories with infinitely many fields, which you can do, for example, by having toroidal compactification or something called omega background. And this will be explained, of course, during the talk. So how does this thing go? Supersymmetric quantum field theory is now very, very old, coming from the 70s, so I can't really explain what it is. In 2 dimensions, supersymmetric gauge theory, or corresponding topological quantum field theory, is nothing more but basically determined properties, vacuum properties, with one function, which is called twisted effective superpotential, and supersymmetric vacua are determined with the use of this function, basically by critical point equation. So if you move this integer to left-hand side multiplied by sigma, there will be shifted function which will have critical points. And the sigmas are, so this W effective is a function of abelian components of scalar field. Now in supersymmetric theories, there is, together with gauge field, there is a fermion, scalar field, and so on. So this is abelianized version, so this is equation which defines, or equivalently this, which defines supersymmetric vacua. Of course, obviously, you have to know how to calculate this W effective, and we will be talking about that. In quantum integrable system, in those that are solved by beta ansatz, beta equations are usually critical points of something called the Young-Young function, y of lambda, where lambda are rapidities, and the equation is similar. And the beta equations defines energy spectrum. Basically, there is formula for energy, and so as a function of rapidities, and rapidities solve this kind of equation. So you evaluate energy on that. There is no theorem that states that for every integrable system which is solved by beta ansatz there is a Young's function, but every case I know there is such. There is one exceptional case that I mentioned here, which appeared in some integrable theories that describes n=4 integrability. It's the big subject itself. It's claimed that there is no Young function for that particular one, that it's kind of suspicious, I don't know why. But for all of the others, there is Young function. Now, statement is, this correspondence states, that effective twist superpotential in gauge theory identically coincides with this Young-Young function under the correspondence, under the beta gauge correspondence. And of course, I mean, these are 2 functions, and up to the diffeomorphisms or some special change of variables, any 2 functions are probably the same. But here, the statement is very precise. The coordinates, special coordinates introduced in the what I call the scalar components of the abelianized components of scalar field are identically the same as rapidities here. So this is written for group UN, but there is similar formula for any other one. And this would not be enough to be very excited, actually. There is a better statement that together with this, vacuum expectation values of special operators in supersymmetric gauge theories, which are called chiral ring operators, this is a commutative ring, coincide with energies. Basically, you calculate now if sigma is lambda, equals lambda, and sigma parameterizes the vacuum, then this will be vacuum expectation value, and they coincide with energies. And hence, of course, we have Hamiltonians, and every spectrum is defined like this. Now, I want to go through this quickly because without explaining these basic statements that I made here, it's almost useless to continue to the more difficult statements I'm going to make. So let me first explain this. So we start in 2 dimensions. As I said, if we want to do something in 4 dimensions, we consider 4-dimensional theory compactified to 2 dimensions. We have 2-dimensional theory with infinitely many fields. So in this particular discussion, 2-dimensional gauge theory doesn't mean it's actually 2-dimensional. It can come from 4 or 5 dimensions or something like that. So we pick a gauge group G, for example UN, and its representation R, which is reducible. So we decompose with some multiplicities in terms of irreducible. So for example, this can be infinite dimensional space. If the theory comes from 3 dimensions, there will be extra index which will correspond to the Kalb-Sublime modes and Fourier modes. So we pick the representation. We say that the matter field's linear representation, gauge field, Young-Mills field lives in a Coulomb branch, gauge sector. So we consider 2-dimensional surface of genus G with n punctures. Now for local coordinates x, we have 4 anti-commuting variables because we are talking about superspace with 4 supercharges. So we have 4 anti-commuting variables. And in physical theory, I mentioned here that we consider the sigma to be just a cylinder. But if you want to do topological theory, then we'll do it like this. Gauge field that we will deal with is in something called vector supermultiplet. It's basically function on a superspace, especially with some conditions, or sometimes it's used something called chiral twisted multiplet, sigma, and it transforms in adjoint representation. So V and sigma are transformed in adjoint representation of group. Matter fields transform in this representation. So we basically have this field, sigma, superfield, this one, and we immediately can write the Lagrangian, which looks like this. Everything was complex, so the Young-Mills section is hidden here. So if you expand the superfield in terms of anti-commuting variables, the components will be various sections. There are some fields with some spin, so the gauge F mu square will be here. This is a Keller potential, so you pick basically any Keller potential and put there these fields I put here. Now, there are 2 interesting objects that one can consider. You can consider holomorphic function of these superfields, which I said were the functions which transform in the representation R. And you can consider any holomorphic function, and plus complex conjugate, of course. And you can similarly consider holomorphic function, W2 I call, of the other fields which were living in adjoint representation. So again, sigma is in adjoint representation, x is in some representation I specify, and this is the most general action you can write with this many supersymmetries. We don't need to know much about this, except that these holomorphic functions will play an important role. The mass term, for example, for the chiral field, so again, x was transforming in some representation which we decompose in reducibles, Ri's. So mass term, quadratic term for Higgs branch looks like this. These mass m's are complex variables, and they live in complexification of the Lie algebra of maximal torus of global symmetry. Now, global symmetry, the maximal symmetry we can have here is a unitary group in this multiplicity space, but in principle, this function can break that symmetry. So if we have a product of unitary groups in this multiplicity space, and this can be maximal global symmetry group, actual one can be less than that because of superpotential, might have less symmetries. Okay. Now, what is topological twist? So we can, the standard law is that the physical theory on a cylinder has some ground state, the vacuum state, and topologically twisted theory actually is completely same as concentrating or studying the vacuum sector of the physical theory. So when Witten invented the term topological quantum field theory, some physicists were kind of complaining that this is not interesting physical theory, why should we be interested? I think it was not sufficiently emphasized that the studying topologically twisted theory was equivalent to studying the only vacuum sector of the physical theory. Of course, we are interested to study the vacuum sector. So there are many twists one can study, but in any case, after topological twist is vector multiplet, which contained, as I said, gauge field, fermion, and a scalar. I denote H, psi, sigma. After twist, gauge field stays what it was, but the fermion becomes one form. It was a spin 1/2 representation, and now it becomes a one form instead of the square root of the. Now the scalar stays a zero form. So one of the things happens that the fermion becomes one form. Now in twisted matter sector depends on this global symmetry group, because there are many choices which depends on this global symmetry group. But basically you have to choose the U1 subgroup, and there are many choices. But requirement that is necessary is that after twist, whatever you do, when you start basically renaming different components that enter in the superfield to have different spins than they had in the physical theory, W of x, again, I remind that W of x was the one which was in the this sector, not this one. Finally, we're interested in this, but now I'm talking about this. W of x should become a one form, which will be known to W0 of x. Q, the supercharges in the superalgebra, after twist becomes one of them becomes a zero form and it squares to zero. This is one of the relations in superalgebra. And Kyle-Lig operators are functionals of all fields such that commute with this Q. So one of the supercharges becomes zero form, it squares to zero. We study all the operators, cohomology basically of this Q operator. And it's very easy to show that such operators that which commute with Q actually form a commutative ring up to the Q exact terms. So these are the kind of ring operators. I will not specify much more, but we are interested in these kind of operators, and they exist in all of them. Now, example of topological again, going back to the old papers written in 80s and 90s, the generic feature is that the path integral of twisted theory reduces to finite dimensional integral, and that's the whole point of doing the topological theory. So it becomes a finite dimensional integral or moduli space of solutions of certain PDEs. And the way I set up this situation, these PDEs are like that. So this is a covariant derivative. A is again a gauge field. We are in two dimensions. This is a z-bar component. And on the right-hand side, we have the metric components I bar. And as you see, there is a 0-1 form here on both sides. And another equation is that the curvature of this gauge field is equal minus the moment map, G-star value momentum associated with, again, the metric defined symplectic form. So this is an equation. I will consider example in a second to be clear. Now, there are, like I said, many topological twists because we have this global symmetry group in the matter sector. We have some choices to make there. Now let's take an example. Suppose X is the following set. So we have one fundamental representation of group, one anti-fundamental representation of the gauge group, and one adjoint representation. I call them Q, Q tilde, and phi. So please don't mix those with the other Qs, which are supercharges. I denoted them with bold Q. Now, obviously, we can write such superpotential. Now, again, this is a fundamental representation, it's not fundamental. This is adjoint in any power we can take as long as S is a half integer. This is a well-defined holomorphic function on the space of these representations. Now, after twist, what's called symplectic twist, one of those twists. It's phi becomes 104, which is phi z. Q and Q tilde will become 1/2 minus S0 forms. Now you see this as important because the superpotential defines what will eventually happen. 0 form, but when you calculate the W, will become 1/4. So more general twists will make phi u comma 0 differentials and the Q tildes others, but the simple one will do this kind of job. Suppose we have no Q and Q tilde, we just have phi, and we pick the metric, just a simple one. Then these equations I wrote before will be something that everybody recognizes, efficient equations. So we consider, of course, them up to the gauge transformation. So this finite dimensional space is solution to these PDEs up to the gauge transformation. So this interesting moduli space called Euclidean moduli space. And again, this is one of the examples because generically this will be a moduli space, it will be interest, again, divided by the gauge transformations. So this is parameterized in terms of the one holomorphic function. What I did there, I picked the function to be 0, so this is a simple case of Euclidean equations. So this is a topologically twisted theory. Now, statement is, no matter what, the topologically twisted theory, eventually, after you do some simple calculations, and I emphasize that this theory actually is Gaussian. There is path integral, or the quantization of this theory does not receive any higher loop correction, so we are dealing with classical action plus the one loop determinant. Everything else is Q exact, and as long as the integrals converge, you can drop them. So everything reduces calculating one loop correction, which is a Gaussian determinant, and furthermore, you can integrate out all non-abelian components of all the fields you have in the theory, because again it will be the determinant only to compute, and eventually, after you integrate out this abelianized action, after you integrate everything which is non-abelian, an entire Higgs branch, basically entire matter sector, you are left with the three fields: abelian components of gauge field, abelian components of the fermion, which became a 1/4, and the scalar abelian components of scalars, which are denoted by sigma. And action will always have a form, which I wrote here. So there is one function, W effective, invariant function on the Lie algebra of our gauge group. You have to take first derivative. This function has to be calculated times the curvature abelian component of the curvature, two derivatives times psi, and certain term here, this R2 is a two-dimensional tensor, or curvature, two-dimensional curvature, or two-dimensional metric, and some function U sigma. So this is an important term later. So effective with superpotential, this W effective needs to be calculated exactly like this function U on the Cartan subalgebra. And of course, this is calculated by Atiyah-Zinger index theorem. As I said, everything is one loop exacted, that the function regularization will give answer. Now, after this is calculated, the rest of the story is extremely simple. This now we are dealing with abelian theory, which is exactly solvable because this path integral now can be calculated. We are integrating over gauge fields and summing over fluxes of the F, and these standard techniques leads to the following answer. So partition function, genetic function of correlators of these special operators which come into with Q. So I'm just add to the action linear term T times O, and this will calculate correlation functions of this operator. So this generalized partition function has a form, certain function to the power G minus 1 times this exponent, where the sigma B here denotes a solution to these equations. Now, where this came from is easy to show. Let's go back to the action. You see, this big, I mean, in simple, suppose you're on cylinder. This is just a simple way to explain it. What is standing here is a time derivative of the one component of the gauge field times something. So this is like velocity, and this is a dot times something. And since we're on a circle, the momenta conjugated to the coordinates gets quantized. So this quantization condition is that the momenta, which is denoted here by this, has to be integer. And that's what's written here. So the path integral reduces to sum over solution to these equations. And as I said, once we calculate the action on previous transparency, this h of sigma, which enters here, the formula for it is extremely simple. So only thing needs to be calculated given this theory is W effective tilde and U of sigma, then we have the answer. Now, what has been written, what has been calculated here, let's go back to make sure we understand. We have, from one side, we have some intersection theory on moduli space of solution to these equations, which contains fission as a particular case. From the other side, we're studying the vacua of the theory given by this Lagrangian. Well, this is difficult actually. So we had this most general Lagrangian. This was the space where the fields live. So we had this most general Lagrangian, and we're studying two questions. Either we're studying the supersymmetric vacua of this theory, or we are studying for a compact Riemann surface with some punctures and so on, generating function of special operators, and in both, which is same as intersection form of the moduli space of solution to this equation, and we have universal formula, which is given by this. Of course, for each case, this W effective is easy to calculate. There is a universal formula for U of sigma. There is universal formula for W effective. This is final answer. Now, the language of physical theory, it goes like that. Target space of effective theory, the sigma model, is disconnected, and this N labels the connected component of which is same as the gauge flux quantization. And the potential is calculated from superpotential by simple formulas. The trick is that in superpotential there are some auxiliary fields, there are some things that actually doesn't enter in the potential of actual scalar field. This is the inverse of symmetric, that we assume that it's not degenerate. So the critical points of potential is related to the critical point of superpotential by just the same formula. So this is supersymmetric vacua, or as in the previous transparency, correlation function of topological fields or intersection forms of the moduli space of solution to those PDEs is given by this formula. In both cases, we have sum over space of solutions of the same equation, these ones that we're interested in. Okay, now what has been done some long time ago is following. If you are interested in now jumping to integrable systems in XXX spin chains, let's say SU2 XXX spin chain on the chain of length L with spins 1/2 and in n particle sector, so this is now the Hilbert space I'm interested. Turns out that the equation I wrote before will be beta equations. Beta equations for this system will coincide with the vacuum equations I just had on previous transparency for U and two-dimensional n equal to supersymmetric gauge theory with L fundamental matter, L anti-fundamentals, and one adjoint, and with twisted masses, which will be related to the coupling constant of spin chain. So basically, there is one scaling parameter, you can set it to 1. If I'm interested in beta equations, basically beta eigenstate of XXZ spin chains, I have to take exact same theory, again spin 1/2 I'm describing now, exactly same theory, but in 3 dimensions, and consider it on R2 times S1, and then the vacuum equations in this 3-dimensional theory will completely coincide with the beta equations for XXZ spin chain, and similarly for XYZ. But I have to go to 4 dimensions and consider it on R2 times T2, and the modular parameter of T2 will be related to the structure, elliptic structure, which is here in XYZ model. Now, as Nekrasov and I managed to explain that this can be done for arbitrary spin groups, any representations, impurities, limiting models, and so on. So what happens is the gauge theory changes. Instead of studying this gauge theory, if you want to study higher spin group, you have to do some other gauge theory, and all this has been understood. Similarly, if you want to study the elliptic Calogero-Moser quantum many-body system or period-order, this also has been explained as four-dimensional N=2 theories on special omega backgrounds, to which I will turn in a little bit later. Okay, now, first example was, let me say a few words in connection to representation theory. I think that I will not manage to finish this talk the way I have planned, but whatever place I stop, probably something interesting will be before that. So let's consider some simple connection to representation. Take N=2 star theory in 2 dimensions, which is the same as the case when you have one adjoint representation. I had drawn before that when you had just one adjoint representation in the matter sector, the theory corresponded to integration of moduli space of Hitchin equations. So the one simple thing you need to add, you have to add the superpotential from the beginning, twisted superpotential. So we will add it just to be quadratic. So you run the machinery I just wrote, and the vacuum equation I showed will be this equation, and you can recognize this equation as beta equations for m-particle sector of nonlinear Schrödinger system, where m there is usually assumed to be I times c, and c is the scaling coupling constant there. Here everything is holomorphic, so in principle all the stuff I'm talking about is holomorphic. This is a choice of real structure, and again the coincidence is when m is equal I times a real number. Now this was the first example treated by Nekrasov and myself, and then as I said, explained by Gerasimov and me in the language I presented basically here. Now interesting thing is, yeah, and I said that this reduces to the integration over Hitchin moduli space. What is n-particle nonlinear Schrödinger n-particle sector? It is nothing more but n non-relativistic particles on a circle with delta function interaction. This is a famous example, famous theory solved early 60s by Elliott Lieb and collaborators, and also Berezin and collaborators. I'm sorry if I don't remember all the names. But this is an example for which the Yang and Yang in late 60s wrote the beta ansatz, because what the previous work was solution on infinite line, and the periodic case was considered by Yang and Yang in that same famous paper where they had beta ansatz. Anyway, so this is the Hamiltonian, which describes this n-particle sector. And eigenvectors are spherical vectors in the representation of degenerate double alpha and decay algebra. This is some modern language after Panchirnik. Now what is this thing? This is basically connected to the representation theory of GL and QP, and the wave functions are limits of the Hall-Littlewood polynomials, which are generalized zonal spherical functions. So if you take Hall-Littlewood polynomial, it depends on parameter t, as was explained yesterday. Yesterday was extensively discussed, so I will not go to too much details. There is a partition mu that enters here in lambda. So the way the wave function is related to this is that you have to take a scaling limit when mu's are written as x divided by epsilon, lambdas are exponentials of sigma times epsilons, and t is also written as 2 pi c epsilon, and send epsilon to 0, which means that you are sending p to 1. So you are having GL and QP for p equals 1. So instead of the prime number, you have 1. Now, what you will get will be the wave function of this. Now, whatever is written here itself is a continuous, so basically what I just said, that there is another system which has Hall-Littlewood polynomial as a wave function, and continuous limit was this one. Obviously the other one can be conjectured, and I was explaining actually this is true, is a discretized version of this. So this will be wave function of discretized version of that. Anyway, now there is, as we were told yesterday, actually again, there is one step to Magnolia polynomials, which are now 2 parameter. If there was degenerate Daha before, now it will be the full one, with 2 parameters. Now, the relation to gauge theory actually before appeared in the work of Gorski and Nekrasov, studying G-mod G-Vesum in a Witten model and Wilson lines there. But as it turned out, there is another way you can get to the system with 2 parameters. If you consider actually a complexified version of G-mod G-Vesum in a Witten model. So this is a model when level of Kac-Moody algebra goes to infinity, you recover previous one. it's basically straightforward and was explained in the paper I wrote with Gerasimov. And partition function in that case will be sum over these equations which are written here. And these are better equations for x-axis spin chains when s goes to minus I times infinity. And actually can be described in terms of supersymmetric vacuum of three-dimensional equal to 0. Now, elliptic case will be omega background, as I just said. And if you want to study the one higher up, the resonance system, you have to study five-dimensional theory. I will not be spending time on this here. Now, I had one slide prepared for those, that's what I was taught by the people who do this subject. But anyway, the way it goes that this nonlinear Schrödinger system in the picture is here. If there is free fermion, this would correspond to Schur. There is Calogero-Moser-Sutherland, which goes up to Jeff. This discretized version, this is McDonald's. What I will be describing later part of the talk will be elliptic generalization of all this picture when I do the omega background. So now I want to switch to the four-dimensional super-Young-Mills theory and algebraic integrable systems. Reason for this is that if I do instead of toroidal compactification omega background, as I said, I will be getting much more interesting examples, and that's what I'm going to do. So we go back to Zeiberg-Witten work, who explained that there is certain prepotential f of a, which defines the effective action in four-dimensional theory exactly the same way, basically, as twisted superpotential in 2 dimensions. So f of a actually plays similar role as W effective before. And this Zeiberg-Witten prepotential was interpreted in terms of classical algebraic integrable system by Gorsky, Griciver, Mironov, Morozov, Marshakov, Martinek, Warner, and Danagi-Witten, in terms of the geometry of periodic tau-dielectric Calogero systems, and then was Danagi-Witten wrote a little broader picture. How does it go? So you take complex algebraic manifold of complex dimension 2n with non-degenerate closed holomorphic form, let's denote it omega to 0. You take holomorphic map where the fibers are polarized aberrant varieties. Basically, we need them to be complex tori. And these H's defining this projection actually with respect to this Poisson structure, this eclectic form defines Poisson structure, the Poisson commute. Polarization is needed actually because the Keller form with restriction of fibers integral class defines the pairing that allows to introduce A and B cycles in the fibers, and we need those. So Zeiberg and Witten defined special coordinates on a base, which are action variables actually, in terms of the periods of one form, theta, such that d theta around the fibers is actually omega is exact, since fibers are Lagrangian, so we have this theta defined up to some ambiguity. So we take this one form, integrate our A and B cycles. In both cases, we will have some coordinate system on a base, but since the dimension, since they are exactly as many A's as half of the dimension of the phase space, A's and AD should be related. These are twice more action variables you have using this defined. So there has to be a relation between them, and the relation goes in terms of the one function prepotential, which these people explained that coincide with the answers that Witten wrote for super-Young-Mills theory. So this is a relation between prepotential in integrable system, classical algebraic integrable system, and prepotential of Zeiberg-Witten. So we're going to deform the story here. So now we take, so this is what we need. This is not what we need from the classical geometry of vacua or four-dimensional theory of called Zeiberg-Witten theory. So f of a basically is something that we define in terms of the classical algebraic integrable system. What now what would do, we take the four-dimensional theory and consider it, the formation of this four-dimensional theory in something called omega background. So this is, the story goes like that, basically. You have action, so the Lorentz group is SO4, which is SU2 times SU2, and it has two U1 subgroups. So you can deform the theory by rotation in one of the planes. So we have two planes here, R2 times R2 if we study R4. So we can introduce two angular variables which are rotations of each of the space. And since this breaks Lorentz group, so the theory will not be Lorentz invariant, but it will be covariant. If we rotate together with this theory will be invariant. So what I will do here, I will consider omega background only with one epsilon parameter when I will not touch this. So this theory now will have two-dimensional super Poincare invariant, and it's easy to show that all the rest of the fields, if you expand in spherical functions with respect to this one, will have mass proportional to epsilon. 1/epsilon. So in that sense, we can actually think about this theory as being in a class of the previous theories I described here, or precisely this will be alternative to Kaluza-Klein compactification. The compactification will be epsilon goes to 0. So now we take, since we are in the class of the previous story, again, there is some effective twisted superpotential in two dimensions, which will describe the vacuum of this theory, and this has to be calculated. And in Nekrasov and I calculated that, and the formulas are very long, I just flashed them. There is explicit expression of this twisted superpotential, which actually starts of prepotential of Zyberg-Witten divided by epsilon plus corrections in non-zero positive powers of epsilon. So the singular term is actually defined, the residue is exactly the same as Zyberg-Witten prepotential. And there are some formulas for this, I won't bother with that. Important thing is to mention is that the way this W is constructed is very similar to thermodynamic beta ansatz in the sense that you have to solve certain integral equation, which is written here for chi, and evaluate functional, which is written here, on solutions of this integral equation, where kernel depends on the super-Young-Bill theory you are studying. The driving term also depends on it. And these are some polynomials, and these coordinates A that compared to Zyberg-Witten periods and so enter as zeros of this polynomial P. So everything explicitly described, and energy is given again by the same formula. So we have to, as before, evaluate the solutions on the critical points of the same kind of equation. The main point I want to emphasize here is that the theory is again two-dimensional. It has some effective twisted superpotential. The way it's actually calculated from the gauge theory is similar to the thermodynamic beta ansatz equation. So we're again in the familiar territory. Now, question would be asked immediately. It's difficult. This doesn't. The question to ask is: so, what is the meaning of this W effective in terms of geometry of this classical picture that we had? So I told you that it starts with 1/epsilon times the prepotential, and this prepotential was defined very geometrically here. So immediate question is, we are deforming this in relations with one parameter epsilon. What is the meaning of this from integrable system point of view? Now from one side, of course, this epsilon is like a Planck constant in a quantum theory. So we actually, by writing this calculated using this formula, this energy formula, and that one, we actually quantize the classical integrable system, which was defining the prepotential. So these are giving quantum answers. For example, if you take the case when the classical geometry was described by periodic Toda, this will give a spectrum of the periodic Toda after quantization. If you take the theory which had elliptical Moser as defining the classical prepotential, this will give the answers for a quantum spectrum of the elliptical Moser, which was not found before, so this was the first new formulas. So the epsilon is like a Planck constant, and this is the exact quantum answer. Looking on these formulas, of course, I mean, mathematically this should be considered a conjecture, although we checked it in every example, any possible way, and this actually does give correct answer in various extensions in various corners. but it has to be considered as a conjecture and proved by some other methods. I don't know any approach to elliptical germoser which would derive same formula. But for periodic torus, there was a solution by Harshov and Lebedev, and we matched it, of course. Just give the same answer. Now, next question you ask, so what is the meaning of this W, or Young-Yang function, in geometry? Well, this is a very good question. And we spent some time with Alexei Rosly and Nikita Nekrasov-Rosly, and I wrote a paper on this. And I want to quickly explain that, although I don't think I will have time. So let's consider an example of Hitchin integrable system. So we go back to now Hitchin. We want to quantize Hitchin system. And we know that for G is 1 in one puncture, for gauge group UN, Hitchin integrable system describes elliptical germoser and this connects to n equal 2 superannuals in 4 dimensions, so this will be a good place to start. Now, the way Hitchin described his integrable system was following. So he takes the phase space to be moduli space of solution to this equation divided by gauge transformation. So this is your M. Symplectic form, this space is hyperkähler, so we can introduce 3 independent symplectic forms. So one would be choose the holomorphic structure to be Z component of gauge field and the bar component of the phi which enters in each equation. And that would be holomorphic symplectic form. And then for giving basis of Beltrami differentials, mu I, this is for SL2 now, PHGL2 I'm talking about, Hamiltonians are given by integrals of trace phi squared times mu. They're exactly 3g minus 3 plus n. Beltrami, so this will be the half dimension of the phase space, which is 6g minus 6 plus 2n. And for g equals 0 and punctures, Hitchin Hamiltonians is easy to show given Godin Hamiltonian. So quantizing this system will be equivalent quantizing Godin Hamiltonians. Now if you pick the complex structure J instead of the complex structure I, where the holomorphic variables will be A plus I phi and A bar plus I phi bar, then symplectic form holomorphism can be written this way. And now this one does not depend on the choice of complex structure. This depends on the choice of complex structure on the more surface. This is independent, this is purely topological. And then the theorem states that the space of solutions to the complex flat connection divided by complex flat gauge transformation is the same space as the previous one that was defined in the whatever by this. So what we were able to show, and I skipped now some parts of it you don't need to know, that the spectrum of Hamiltonians defined, these quantized Hamiltonians, can be explicitly calculated using the relation with gauge theory I was explaining before, simply by defining certain Lagrangian submanifold in this second space, here. So this is also some symplectic manifold, as I explained. So we are looking in the moduli space of complex flat connection, certain Lagrangian submanifold, details I have to skip unfortunately, and that Lagrangian submanifold appeared in many work before, in the work of Benson-Drinfeld, in the work of Sklianin, and so on. And claim of paper with Rosly was that W effective is a generating function of that special Lagrangian submanifold called Lagrangian submanifold of Opers in a very particular coordinate system that we had to introduce. So this work of Nekrasov-Rosly in my mind reduced the question which I asked here, what is the meaning of W effective in the geometry of the Hitchin moduli space, to the question of introduction of special coordinates in the moduli space of flat connections, which is the same as Hitchin moduli space in a different holomorphic structure. And why these particular coordinates have to be introduced, I don't have explanation. Although these coordinates are very natural, they are complexified version of Feldt-Rizzo coordinates for case of SL2, and also very well match the work of Teschner, where from the conformal field theory side, the same kind of formulas appear with a different meaning, but very close to this. Unfortunately, I don't have time to describe some algebraic structure which is based on my most recent paper with Pestun and Nekrasov, but I am happy to answer the questions on this, because what the paper with Pestun and Nekrasov was able to accomplish was to reduce the meaning of all the equations I was showing before to certain Q character equations, and but I'm happy to answer questions if thank you.
I think we have time for one question. Any question?
Yes.
So you had given the example of x spin 1/2, and my question was, what if you have the inhomogeneous? Do you treat any of the inhomogeneous?
Right. All these parameters that you can introduce on the integrable side, impurities, inhomogeneities, and everything, have a meaning in the gauge theory side, and also quasi-periodic boundary condition you might want to introduce. They have meanings. They have name of Faleolopoulos term. The impurities and inhomogeneities are related to the masses of the fields in the sector. So basically, if you wish, setup is such that whatever you do on the integrable side, I can pinpoint what it corresponds. What I cannot do is to explain what is the meaning of the excited states in gauge theory. Because all the states of integrable system are described in terms of the ground states of gauge theory. But gauge theory has huge sector, and that one I don't.
Your last next speaker again.